So using the formulas we know for surface area and volume of a box, it should be that the surface of the box, if we just think about it for a second, surface of the box, it has 6 sides, so you would have x squared for the base, x squared for the top, or the cover. So you have 2x squareds. Each of the 4 sides surrounding is x by y. You'd have 4 of them, so you'd have 4xy. And this all equals 600. I'm just replacing the letter S of surface area with the actual formula for it, given the variables we've chosen here. Volume of this box should be length with height multiplied together, so you'd have x squared y. Okay, so this function here, v equals x squared y, is called the objective function in these types of problems, because it is your objective to, in this case, maximize. It could have been a minimized problem, but it's not. It is your objective in this case to maximize this particular function. We want to get x squared y to be as large as possible. Over here, this function, or this equation, is called a constraint. And a lot of these problems have both of these simultaneously, and you need to figure out what they are. You need to figure out the objective function, the constraint. Once you have that, the rest is basically algebra and the calculus we've been doing so far. So a lot of the difficulty of the problem is not so much in the method to follow, but in what we just did, the setup. The setup of the problem can be notoriously difficult for a wide variety of problems. Some of them are quite simple, but they quickly move through the problem set into much more difficult problems where the setup is the crucial feature that a person needs to figure out. And this one's not so bad. But if you've never seen this before and you were given this problem, this could be extremely difficult to figure out how to proceed if you have not seen something like this before. All right, so now we have this. The objective function, the constraint, will be used in tandem. The reason it's a constraint is because you can see that you have the variables here and they're equal to a particular value. So therefore, there's now some natural relation between x and y. And if I pick up an x value here, y would be constrained to be something in particular. If I pick up a particular y value, x would be constrained to be something in particular. So it's a constraint on the variables. All right, so how do we use them in tandem? Well, the main point is this. My objective function is the volume. I want to maximize volume. So what should I do? Well, we know from previous sections dealing with relative extrema, right? To maximize V, we should set, dV d something, right? I'm going to write x here in anticipation. dV dx equal to 0. Okay, so what's the problem with this? Right, we know that whenever we set the derivative equals 0, we're finding a relative extreme location. Possibly we're going to find critical values where the extrema, if there are any, have to be located. Now I chose dV dx here because I know what I'm going to do in the next move of this problem, but it could have been dV dy. Right, because this is the real conundrum at the moment, is that the volume is a function of 2 different variables. Right, it's a multivariate function, and in the course so far we've had no multivariate anythings. Everything's been single variable calculus. So what we're going to try to do now is render the volume function single variable. Okay? Now obviously I've chosen which one I want. I would like v to be a function of only x at the moment, and I'll mention why I'm picking that in 1 second, as opposed to being just a function of y. But the main point is, though, you have to select which variable you wish to keep and which one you wish to discard. And the way you discard it will be to use the constraint function, the constraint equation, to substitute in for one of these 2 variables. So for example, I'm going to go with keeping x here. So that means I need to substitute in something for y. So that's where this will come into play. I see a y here, I'm going to solve for y. Solve the constraint for y. All right, so if I just subtract 2x squared from both sides, and then divide by 4x, that should get y by itself. So I'll have 4xy equals 600 minus 2x squared. And then dividing off by 4x, we will have isolated y. Y will be 600 minus 2x squared over 4x. Now we can clean this up just a little bit, and we probably should, so let's do that. We can take out the common factor of 2 from everything. So we'll have 300 minus x squared on 2x.